Hi, everyone. My name is Michał Dominiak. I work at Nokia Networks in Wrocław, Poland. And today I'd like to talk to you about Variadic templates, but more from the code generation side rather than type generation. So I'm going to assume that most of you are familiar with templates. They are nice, right? They allow us to write code once, use it with multiple types. They also allow us to do some slightly less nice for the users things like this, which breaks the expectation, but let's not talk about that anymore. So we can, for example, write this function. This is, in fact, the standard min function, and it returns the reference to the smaller value passed inside. So frankly, I'd prefer this function to look like this, because it's nicer, doesn't give me potentially dangling references and so on. And to avoid having enormous amounts of code on my slides, I'm going to write this as this, and let's just assume that all the boilerplate from this slide is also present whenever I write something like this, just to be clear. So that's nice and all, but we want to have the minimum value of multiple values. And ideally, we wouldn't call something like accumulate to fold on all the values. Partial application is also a use case where we need something far more flexible than just C++ 98 templates. And let's not talk about some mistakes that were made in the library in the past. And what about types that are parameterized on an arbitrary number of things? The primary example we will be using today is variants, because they are nice, they are useful. Okay, so about variants. There's this type called boost variant, and some people don't really like it for several reasons. And one of the reasons is that its signature, its declaration, looks like this. How many of you can read that? All right, and all this boost preprocessor machinery expands to something like this. I consciously didn't make an effort to fit into this slide. So, okay, you can configure how many types you can hold in a variant via a macro. It works, kind of, but whenever you get an error at compile time, it spews something that makes the output completely unreadable, especially so if you have a variant of something that has a variant inside. How many of you worked with types like that? And how many of you liked the error messages? Yes, I thought so. Okay, so there is another approach that was used for variable number of template arguments for types or functions before C++ 11. It was something like this. It's very nice, it's very functional, so we have a list. The list is either nothing, that's the tail above there, or an element, in this case a type, followed by a list. And it looks something like this. So this was useful, right? How many of you used something like this? Okay, I see some hands. All right. How many of you had to debug a piece of code that used this and had 30 arguments in the list? I had that pleasure, and it's not very nice to look through backtraces of all this. And notice that there is a space between the closing brackets for the template arguments, because this is pre-C++ 11. And now imagine 30 of those printed one after another. It's not very nice. So there's a nice feature in C++11. It's called Variadic templates. So you can write something like this. It's a function that takes any number of arguments of any types. You can call it in whatever way you want to. You can declare a type that's parameterized by any number of types. You can use that with any number of types. That's nice. Here's how you could implement the main function. And once again, I'm ignoring all the perfect forwarding boilerplate here. And this is recursion. We recurse, and of course, we need the termination condition, so I chose this one, because one argument is nicely generic for the interface. And what happens when we actually call this function? So this is a rough approximation of what happens, not an exact one. So the compiler sees that definition and substitutes all the arguments. And what happens with the variadic pack there, the tail ... that was in the definition, is that it gets expanded into a comma-separated list of elements in that pack. So this is the overload for 4 ints. This is the overload for 3 ints that's requested in the previous one. And finally, the overload for 2 arguments where the pack is empty. That's also a valid situation. Okay, that's easy, that's nice, right? So there is multiple things that can be done with variadic templates, and recursive techniques are not particularly interesting. So let's move to something else. Tuple unpacking. How many of you have been to STL's talk about tuples? All right, you will be slightly bored in this part. Yes, I see you, Steven. Okay, so a tuple is a generic data structure containing some values of some types. This is a tuple. It has the following interface. You can create it. There is a helper called make tuple in the standard library. It creates a type that uses all the arguments. And there is a function called standard get that allows you to extract a value from a tuple. So I'm not going to say anything for a moment. STL is sitting over there. All right, let's do something useful with this type that's not very nice for some people. We will use it as, like, the problem that I'm going to solve in a way is to use tuple as generic storage, and we have a function called passed later, or there's many variants of this problem when you have all the arguments for function call stored in this thing. So it's easy to do when there is no genericity. You can just standard get every argument by hand, but we can do better. But to do that, we need to generate all the integers from 0 to number of arguments -1. There used to be a time where this slide would be like 5 of them, or a 20-minute talk at a conference. There is a nice tool for exactly this purpose. It's called integer sequence. There is a alias for integer sequence for standard size t called index sequence. There is a function called make index sequence that does exactly what we need for this purpose. So this is how we do this. If at any point you have any questions or anything is unclear, please ask immediately. so we can all follow everything. So there's one caveat with this technique. It's that we have to have a wrapper for the call. Because we somehow have to deduce the index sequences arguments. But it takes some boilerplate. It's not very nice in some situations where you would like to contain everything within a function and use lambdas, but it's doable. And there is a standard library function in C++ 17 called apply. Is it apply? It's called apply. That does exactly all this that we are doing here. All right. That's one of the uses. The next use is kind of simple, but touches a problem with using Variadic templates in C++. So who here does not know what SFINAE is? Okay, it's it's not really obscure, but it's like a weird language feature that allows you to have an error that is not an error. So there is this type that contains a member type alias called type only if the Boolean argument is true. So any access into the member alias for enable if when the first argument is false results in a compiler error or not. So this function does not participate in overload resolution if interesting trait is false, because we are trying to use a type that is not there. So this is a way to write SFINAE for functions. It's not particularly useful for non-void functions or for functions, well, for non-void functions where you know the type, you can just pass that as a second argument to enable if and everything works. If you want to use type deduction though, not so nice. So you can write this. It does basically the same thing. There's many variations of this form, like some people write type name equals type name std enable if instead of this, but whatever. It's all the same. So there's something else we can do, because this last form has one little weird problem that you may or may not care about. It's that the 0 ends up in the type name. So every time you print the type in whatever ways, you get the 0 that does nothing as a template argument. So we can write this. This pack will always be empty because there is no way to deduce the values for it. Well, unless you explicitly provide the template arguments for the function, but that's silly. So this is nice and all. You can also do better, shorter, and do something like, oh, I'm missing colon type on this slide, sorry. So basically create a pack of void pointers instead of integers. But there was a compiler back in Clang. It was there for 4 years before a person fixed it. It was the state before February, so slightly later a comment appeared under that bug report that this actually has been fixed for 5 months already. So I lied in my previous, the previous time I gave this talk, because it has already been fixed, only not released. And the person who fixed this was Richard Smith, which is kind of appropriate, I think. All right, so great, we can use this in any compiler we can. Great. There's people who refused to make their libraries compatible with Clang by doing the equals value version of this SFINAE form. So I'm very happy that I can just use those libraries on Clang now. All right. There's another thing that we can do. We can expand more complex expressions. And we kind of have seen that already, but let's see what's going on here. So there is a few contexts where you can do variadic pack expansion. And it's a consequence of the fact that variadic pack expansion is really just expanding the pack into a comma-separated list of things, of types, of expressions, of whatever. And there's a few places where it would be nice to be able to use those. With declarations, particularly with using declarations when, for example, trying to pull an overload from all the base classes we have. There was actually a paper that went through EWG for allowing this, but it got stuck in CWG, so I hope we will get this in C++ next. And we cannot just create a statement out of a pack of expression, like not even parenthesizing the pack expansion helps, because what if the pack is empty? You cannot have just a parent, semicolon, that makes no sense. So not everything is easy with variadic packs of expressions. So we want to call a function per every argument. Ideally, we would write something like this, and it would compile, but it doesn't. And for somebody who doesn't know what's going on, the error messages are very confusing. So expected expression, there's an expression there. Expected semicolon before the ellipsis, but the pack is not expanded. Like, I'm expanding the pack, so the pack is expanded, and I have semicolon after that. No, it doesn't work. And the compiler doesn't help explaining why it doesn't work and how to make it work. All right, let's make an attempt to actually do this. Let's write a function that basically swallows any value that's passed into it. There's nothing with it, just captures a reference. That it does literally nothing. And so we could try to write something like this. Let the swallow call grab all the return values of bar calls, and everything should work, right? Well, there's one caveat. If bar returns void for any of the arguments, that doesn't work. So we would write something like this, which doesn't look so nice anymore. I'm using a comma expression there to make all the expressions have the value 0. So there is no void among the arguments to swallow. All right, so that should work, right? How many of you know why this doesn't work? Okay. All right. So let's try a concrete example. We will print every argument. Actually, in this case, this 0 is not necessary because there is a value returned by the previous expression, but just to show the general case. And we call the function with 1 to ABC. And it should print 1 space 2 space ABC, right? Yay, mission accomplished. Not. All right, let's try something better and something that actually works. The problem here is that the order of evaluation of function arguments is not defined to be from left to right or from right to left, or it used not to be defined to even not interleave. As of C++17, it's defined that every argument is fully evaluated separately. There is no interleaving between the execution of the expressions initializing the arguments. That's nicer than before, but it still doesn't get us there. So let's try something. This isn't strictly necessary. I like this because it shows that we don't really return a value, just something to fool the type system into thinking that we are returning a value. Ideally, void would work, but... And we slightly change the definition of swallow. We make it a structure with a constructor that looks exactly the same like the function previously. And the thing we need to do is just construct an object of the type instead of calling a function. The trick is that C++11 specified that for braced initializer list, the order of evaluation of the arguments is from left to right, always. So this finally works. So some people use just a array of integers instead of separate type and write "0" everywhere. It's a matter of taste how exactly you do this. I prefer writing it the way I showed you because I think it conveys the intent better, and most of the function I write, the AI suspect, will be used this way, return something. So it's not a problem for me. But whatever works for you, really. All right. So there's a use case of something that tries not to use visitors that are implemented outside of the function. So virtual functions have pretty much the same problem, only the code tends to be in the right place instead of some random place in the file before the function that actually does the visiting of a thing. Virtual functions are not nice, they are not particularly fast. We can do better, provided that we have context for lambdas. And this time around, for those who somehow saw the previous iteration of the talk, I actually have some assembly in the slides. Show the difference. OK, so the basic observation is that lambdas are expressions. So since we can expand a pack of expressions, we should be able to expand a pack of lambdas, right? So we should be able to write something like this. OK, so variant is something like-ish the standard variant. It has a function called index that returns the index of the currently active member of the variant. It has an associated function called get that allows you to get the member of the variant, provided it's active. And index of is really just a meta function that takes the index of t in the pack. So the probably confusing for some people line is the line using t equals ts. It looks weird. There's an unexpanded pack there, but it's expanded outside of the lambda function of the lambda body. So it's the only place in the entire thing where there is an unexpanded pack. So this should expand to a pack of lambda expressions for every type in a variant that extracts the value from the variant and prints it out. And then we create an array of function pointers to those lambdas. Since we don't capture anything, those lambdas implicitly decay to function pointers. And using that call table, we just call the appropriate function, passing the variant in. This is great. This works almost. If you look back at the slides, and look at the name of the guy who reported the previous issue, you will notice it's the same guy, and I know that STL probably knows the name. I expect so. So this time there is no happy ending, because as far as I am aware, and I think I checked yesterday, the bug isn't fixed in GCC. And the error messages GCC gives are really confusing, because they basically say the same thing as for the attempt of expanding a pack of function calls just as a statement. It says, oh, here you have an unexpanded pack. And at the end of the lambda where the ellipsis is, it says, there is no pack to expand. So it's very confusing, but thankfully we can make a workaround for this. And having read some implementations of Variant that use out-of-line visitors, and having read my own implementation of Variant that uses inline visitors, even with all the boilerplate that the workaround to make this work in GCC requires, I still think this is worth it, because you don't have to jump across multiple places to see what is actually going on, and it's kind of easier to follow the code, I think. All right, so we'll use this guy. It's an identity meta function. It's supposed to be used as a value that passes the type together with it. So the previous function, when turned into a version that compiles with GCC, looks something like this. The general idea is the same, only now the line that creates the type alias is slightly uglier, like type name, decal type, type type. There appears to be slightly too many instances of the word type on that line, but you write this once, then you copy-paste it everywhere, it's not that bad. I'm serious. Okay, so generator is a generic lambda that takes an argument. The argument will be an instance of the meta function that we saw on the previous slide. And then we return a lambda that does basically the same thing. So the generic lambda just provides a context to allow an easier extraction of the single type from the type pack. And then we call generator for every type in the variant with an object of type ID of these. Is this comprehensible to everyone? All right. So at some point, I was given a question whether those two are equivalent, like whether the workaround for GCC introduces any costs. No, it doesn't. It's just function pointers, and the return value of generator is an empty type. And if you were at one of the optimizers talks, it was, I think, 2 days ago, there was an example of LLVM RI where returning a lambda basically returns void. It just conveys type information, and since that's all that's required to get the function pointer, there's no overhead. Although, there is one interesting thing. So, as I said, there's going to be some assembly in the slides. Let's take this program. It does basically the same thing. Like, it's not important how exactly it's implemented. It uses the same technique to print the size of if, or ith, rather, element of the pack of the arguments of foo, where I is passed at runtime. And I in main is volatile, because otherwise in some situations the compiler got way too smart. Okay, so I mentioned const_expr lambdas before. So const_expr lambdas have been implemented in GCC 7. And the output from GCC 6 is something like this. So for those of you who don't read assembly, the first three repeating blocks are the lambdas for every type. So the first one prints 4, because that's the size of int. The second one prints 4, because that's the size of a float. And the last one prints 8, because that's the size of double. Next we have main. We have code for main. So first we set up the stack, then we set up the volatile variable we are using. And the next one we are doing is, the next one the compiler is doing there, it's fetching the guard variable for the static array inside the function. Because function local static variables in C++ are thread safe with regards to initialization. So there is a guarantee that no two threads will initialize the variable at the same time. So it's checking whether the array has been initialized. If it has not been initialized, it makes a jump. And otherwise, it follows with just a call to the appropriate function and returns from main. Next, it first acquires a mutex, basically, checks whether the variable was initialized in the meantime. If it has been, then it just jumps over to the code that actually does something. Otherwise, it initializes the array and jumps to the code that actually does something. All right. That's not very bad after the first call. Like, it's not nice, but we can live with this. Only there is a better code that's generated for this. One note is that Clang generates basically the same code, only it uses SIMD for initialization of the table. This is the output from GCC 7. This time it almost fits on the slide. So it generates the functions, and then it calls the functions. It can statically initialize an array. And I think this is directly related to the fact that lambdas in C++ 17 are implicitly const_expr whenever possible. But do note that I did not have to change the code to say const_expr on the array of function pointers. So this is very nice. I hope it comes to Clang soon. Like, soon. I like this. All right, we have some techniques that we can use. And we are going to use mostly the last one to implement a variant type. There is this guy in the standard library. And it's useful for providing storage for a value of a type without actually declaring a variable of the type. So the number one source of bugs related to aligned storage is the fact that you have to write : type. I did this on numerous occasions. It's easy to forget, so thankfully there is an alias in C++ 14, I think. Yes. I can hear you. What is the failure mode? If I forget to write type, okay, there is no compiler error. No. This structure is a structure. It's an empty structure, so it has a size of 1. And then you try to construct an object into the storage of the structure of size of 1. And your variable is probably larger than 1, so you write outside of your class, which is not very nice. And not trivially to debug, usually. Right. So this is the basic idea. We have aligned storage for all the types. So we need aligned storage with the maximum size among all the types and one that fits all the alignment requirements of all the types that we can store. And then we have a member that contains the index of the currently active member of the variant. This is the simplest constructor that can possibly exist for this type. We get some value, and if that value is somewhere amongst the possible types we can store inside the variant, we just construct the type, we move construct it at the storage we have. How many of you don't know the new syntax I used here? Everybody knows it. Oh, you raised your hands for we don't know this? All right, so this basically takes a pointer and constructs the object in the storage that's pointed to by that pointer. It's implemented as a overload of the operator new that just returns the argument. All right. The copy constructor. There's, of course, I'm going to ignore such weird things like exception safety for the purpose of the slides. And I'm going to ignore such things like move operations. So this is all in the beautiful world where everything succeeds and copies are cheap. All right, so this is basically the same trick with lambdas that we've used before, together with the workaround for GCC. We grab the object from inside the other variant. We construct a copy at our own storage. Is this understood? Yes. I can't hear you. Can you use the microphones for the questions? Because to avoid shouting.
Why are you repeating this code and not simply calling visit function with the generic lambda? The visit functions that you will write on the next slide, I guess.
The visit function that I call fmap, and I will have in 2 slides. Okay, is your question, right?
You can, instead of writing all this,
this
you
is,
can just...
This is the implementation of something that is pretty much almost the same as standard variant, and everything that's around the standard variant. So you could also ask a question, why am I re-implementing variant? The answer to that is because I don't like the empty state inside the variant and some of the lack of the requirements in the standard variant, but that's not important. Okay, this is copy construction. So copy assignment is slightly longer, and we have to do double dispatch because we have 2 variants, then can have 2 different active members. This is the only point where the workaround for GCC gets really not nice, because it adds like 6 lines of code, but whatever. And again, this is completely ignoring exception safety. Because once you try to remember about exceptions, it gets way more complex. So this is copy assignment. So we first distract the element we are holding, and then we construct a new one. We cannot really copy assign the objects. We could do that only if the types held by both variants were the same, but that's weird special cases that we don't need. Distraction, pretty much the same. I just called it distractor. And there's two more functions that are useful. The first one is called get. There's many different things you can do when the get is invalid. I chose to throw an exception. I guess sometimes you might want to terminate instead. Like, I have no idea what the standard variant is doing when this happens. So I don't know. I would have to check. And the last function, where I do this. Last time there was a lengthy discussion that whether the name of the function is correct or not. I would appreciate if we could not repeat that discussion here. Thank you. Like, otherwise, the result of the discussion was that the proper name for the function would be nmap, but that's a command line utility, so no. So the result type I have to compute beforehand. It's going to be a variant that's able to hold a value of any of the types that can possibly arise from calling the function on a type inside the variant. If you are interested in how this actually looks, I can show you. So when we have the result type, we just do basically the same thing. Only this time the functions that we are using will actually return a value that we have to return from this function. And for the full implementation of all that I have in my variant, you can go there. Or if you are interested in it, I can show it to you. And that's all the slides I have. Thank you.